Water coning in oil wells. Petroleum accumulations. Origin of petroleum. Migration of petroleum. Petroleum reservoir rocks. East Texas trap is the Austin Chalk Reservoir. Woodbine sand. Naturally occurring salt water beneath the oil. Migration of petroleum. The natural property of petroleum is to rise. The petroleum will rise until it is stopped by a trap. The trap in East Texas is the Austin Chalk. The Austin Chalk has a low permeability and prevents the upward rise of the petroleum. The permeable porous layer underneath the Austin Chalk is the Woodbine sand. The low porosity of the Austin Chalk halts the upward migration of petroleum. Origin of petroleum. All petroleum was formed over 1 million years ago. There is no new petroleum. Oil and gas originate from organic matter and sedimentary rocks. Dead vegetation in the absence of oxygen ceases to decompose. It accumulates in the soil as humus and as deposits of peat in bogs and swamps. Peat buried beneath a cover of clays and sands becomes compacted. As the weight and the pressure of the cover increases, water and gases are driven off. The residue, even richer in carbon, becomes coal. Out in the sea, a similar process takes place. A rich banquet of marine life is eternally falling in a slow rain to the bottom of the sea. Vast quantities of it are eaten, some of it oxidized, but a portion of the microscopic animal and plant life escapes destruction and is entombed in the ooze and mud on the seafloor. The organic debris collects in sunken areas at the bottom and is buried within a growing buildup of sands and clays and more debris until the thickness of sediment attains thousands of feet. As the sediment builds, bacteria and pressure of deep burial begin their work. Bacteria take oxygen from the trapped organic residues, breaking them down molecule by molecule into substances rich in carbon and hydrogen. The extreme weight and pressure of the mass compacts the clays into hard shells. Within this deep, unwitnessed realm of immense force, oil is born. Water coning in oil wells. In the case of water production, high reservoir pressure, low or no tubing pressure. Water and gas coning. Coning is a production problem in which gas or bottom water infiltrates the perforation zone in the Neal reservoir areas and reduces oil production. Gas coning is distinctly different from and should not be confused with free gas production caused by naturally expanding gas cap. Likewise, water coning should not be confused with water production caused by rising oil-water contact, WOC, from water influx. Coning is a rate-sensitive phenomenon generally associated with high producing rates. Strictly a near wellbore phenomenon, it only develops once the pressure forces drawing fluids towards the wellbore overcome the natural buoyancy forces that segregate gas and water from oil. The impact of coning. Coning is a problem because the second phase must be handled at the surface in addition to the desired hydrocarbon phase, and the production rate of hydrocarbon flow is usually dramatically reduced after the cone breaks through into the producing well. Produced water must also be disposed of. Gas produced from coning in a well may have a market, but also may not. In any event, production of gas in an oil well after the cone breaks through can rapidly deplete reservoir pressure, and for that reason may shut in the oil well, may force shut in of the oil well. Several strategies may apply to wells with a potential to cone. One is to try to predict the rate at which a well will cone and produce at a lower rate as long as possible. Our optimal economics may result in producing Water coning delay criteria. Water and gas coning is a serious problem in many oil field applications. The production of coned water or gas can reduce oil production significantly. Therefore, it is important to minimize or at least delay coning. In reservoirs with bottom water, vertical wells are normally completed in the top section of the pay zone to minimize or delay water coning. Of course, this assumes that there is no gas cap. Similarly, in a reservoir with a gas cap, if there is no bottom water, a vertical well is perforated as low as possible so that the perforated interval is as far away from the gas cap as possible. If an oil reservoir has both gas cap as well as bottom water, then the vertical well is perforated either near the center of the oil zone thickness or below the center toward the water zone. This is because coning tendencies are inversely proportional to the density difference and are directly proportional to the viscosity. The density difference between gas and oil is normally larger than the density difference between water and oil. Hence, gas has less tendency to cone than water. However, gas viscosity is much lower than the water viscosity, and therefore, for the same pressure drawdown in a given reservoir, the gas flow rate will be higher than the water flow rate. Thus, density and viscosity differences between water and gas tend to balance each other. Therefore, to minimize gas as well as water coning, preferred method is to produce at a slow rate for the entire life of the well. Coning cause. Water has a higher flow rate, so slower oil production rate is preferred. The occurrence of water coning has been known for over 60 years. In thin oil or gas pay sections, the presence of an oil or gas water contact hinders production and often causes early abandonment of the afflicted well if a completion is even attempted. Even when relatively thick pay sections are found, the encroachment of water when a water drive is present will eventually pose serious water coning problems. This water is often corrosive, expensive to separate from the oil or gas, and is costly to dispose of. The theory of water coning has been discussed by a number of authors. Briefly, water coning to the producing interval in a well is due to pressure gradients resulting from the production of fluid from the reservoir. These pressure gradients will cause the water to rise toward the bottom of the producing interval. If a water oil or water gas contact exists, the tendency of the water to cone is offset by gravity forces. Since the water has a higher specific gravity than oil, a balance then exists between two forces, gravitational forces arising from the difference in specific gravities in the oil and water, and the pressure gradients causing the flow of fluids to the wellbore. If the pressure gradient exceeds the gravitational force, water coning to the wellbore occurs and water production results. Through the years, considerable thought has been given to water coning problem. More than 50 U.S. patents have been granted to inventors on the subject. A relatively complete literature review of the water coning problem has been made. A number of these patents hold considerable promise for the solution of the partial solution of the water and our coning problem. Very little has been written describing field tests. A study experimentally and analytically verifies the benefits of water and our gas coning is a serious problem in many reservoirs with wells producing from an oil zone or underlying gas cap overlying an aquifer. Both coning occurs in a well on production when the water or gas zone moves upwards the wellbore in form of a cone. Eventually, the water or gas breaks through the well and water from the aquifer and our gas from the gas cap is produced along with oil. The water or gas production increases progressively after breakthrough time and may reduce significantly the crude oil production. The main factors affecting the water and our gas coning tendency are the density difference between oil and gas, water viscosity, water and oil gas, formation permeability, pressure drawdown, flow rate, etc. More specifically, the tendency of a fluid to cone is directly proportional to the density difference between the fluid and crude oil, but inversely proportional to the fluid viscosity and reservoir permeability. The water and or gas coning can be reduced by decreasing well production rate, improving the productivity of the well, Using selected parts of penetrating the well at the top of the reservoir in the case of water coning, bottom of the reservoir in the case of gas coning, and close to the center of the pay zone in the case of simultaneous water and gas coning. Be completing the well at a different elevation to increase distance between the gas contact and the perforated interval. Most research efforts in the area of water and gas coning have concentrated on estimating the critical oil rate in post-breakthrough well behavior. In the subsequent parts of these studies will be discussed. One of the first papers published on the coning phenomenon was by Muscat and Wyckoff in 1935. In the case of water being produced at the surface, water production will make the tubing heavier. Water in tubing can reduce tubing pressure to such an extent that artificial lift may be required. With the low tubing pressure but reservoir pressure maintained at relatively high level, bottom water can be pulled into a well by excessive producing rates. Coning may occur in either oil and gas well as indicated by increasing water-oil ratio. Problems of coning can generally be improved by reducing the production rate. Production of water from an oil or gas well can cause permeability reduction. High production rates will tend to pull water in the well due to coning.